Hey everybody, welcome back to Math 20-1. We are still in the Inequalities and Systems of Equations unit. Today we are going to be looking at linear and quadratic inequalities in two variables. Remember, at the beginning of your notes, there is a list of things you should be able to do or know by the end of the lesson. If you have any questions about any of these things as you're working through the lesson, be sure to get in contact with your teacher. They would love to hear from you. Let's get started. So up until now, we have mostly looked at functions or equations. Now we are going to be looking at inequalities. Now, inequalities are not concerned with a specific expression that equals, but rather an entire set of values that could make the inequality true. This means that referring to all the values of y that are greater than some other value of y, or all the values of y that are less than or equal to some other values of y. And these are some examples, and let's go into what that might mean. For instance, if y is less than 3x squared plus 4, well, how can probable So you can probably reason that there are many values of y that satisfy this inequality, even at just one specific value of x. Let's look at just one x to get the idea. Let's choose the easy one, x equals 1. At this x, what y value does the inequality become true? Well, if y is less than or equal to 3 times 1 squared plus 4, well, 1 squared is 1, 3 times 1 is 3, and then plus 4 gives us 7, we now end up with y less than 7. Well, there's many values of y that are less than 7 that will make this inequality true. And not only is there many, there's infinitely many values that are going to make this true. So remember, in inequalities, there can be infinitely many. For just an example, we could have 1 and 6, because 6 is less than 7. We could have 1 and negative 6, because negative 6 is less than 7. We can even have negative 1 billion. And all of these points would be included in a region of XY combinations that make the inequality true, or in other words, satisfy the inequality. Now, these regions that we're dealing with, these are called solution regions or solution sets. And rather than individual points, there's a lot of values that can satisfy the inequality. In particular, we're going to notice that these regions are areas. So let's look at an example. To satisfy the inequality means that the statement remains true once values for x and y have been substituted. Indicate if each of these points satisfy the linear inequality. Note, these are often called test points, and we're going to be using test points to check to see if the point lands in this region or not. So with our point 1 and 2, we're going to substitute 2 for the y. and we're putting in 4 times 1 minus 2. So we get 2 greater than equal to 4 minus 2, which is 2. Now the statement is 2 is greater than or equal to 2. Well, it's equal to 2, so that is true. Let's do the next one. So the y is 2, but this time our x is 2 as well. So here we get 2 times, 4. 4 times 2 is 8. 8 minus 2 is 6. 2 greater than equal to 6? Well, that's a big no. The 2 is not greater than or equal to 6. So we can say that 2 and 2 is not in the solution set region. Let's look at 1 and 0. So substituting our 1 in here. Now this was just like the first one. So 0 is greater than equal to 2. Again, we have another point that is not in the solution set region. So if we have entire regions made up of points that solve the inequality, how can we show this in a graph? Because before we used to show it in a graph by drawing lines or drawing a point. Well, let's look at that and see what we come up with. So before we get into it, we need to review some graphing skills. Now, when we're drawing a linear graph, 2 main strategies are used. Both work, but one you're probably going to like sometimes more than the other, depending on the circumstances. So let's look at a linear function of the form y equals mx plus b. Now recall that m is the slope of the line. And remember, the slope can equal the rise over the run, the change in y over the change of x. And b is the y-intercept of the line, and that's where it crosses the y-axis. So we're given for an example, we're given the graph of a linear equation shown below. We are going to try to graph this using 2 strategies. The first one is use the y-intercept in the slope. So you know the y-intercept from the b value, which is 3. So we're going to locate that on the y-axis. That's -3, my bad. So we come down to -3, and we draw our dot right here. Well, we are going to go for a little walk at this point using the slope. Remember, the slope is rise over run. And on any given line, the rise is how far we go up or down. Let me change my color. And how far we go across. So we're going to go for a walk 3 units up and 2 units to the right. And when we do that, we're going to place a point. So we go up 3 over 2. Up 3 over 2. Up 3 over 2. Now we could also go in the reverse direction because 3 over 2 is the same as negative 3 over negative 2. So I can go down 3 over 2, and notice that these line up to make a straight line. So we'll go ahead and get our straight line out. And joining them up. So that's using y-intercept and slope. Well, let's look at the next strategy. The next strategy is to use the equation to find 2 points. You can use the y-intercept of b, but then you can substitute in an x and solve for what the y must be. This will give you 2 points that you can connect with a straight line. Okay, before we get going, we are going to review some graphing of linear functions in Math 10C. So 2 main strategies are used, and both work. So you can choose which one is either most convenient or the one that makes the most sense to you. So let's start by reminding ourselves that y equals mx plus b is the y-intercept form of a linear equation, where m is the slope, and remember that the slope is considered either the rise or the run, which is the change in y over the change of x. And if we look at a graph, we know that for between any 2 points, we can have a rise or a run. And then the y-intercept of the line, which is b, well, that's where it crosses the y-axis. So let's look at an example. Graph the linear equation below, y equals 3 over 2x minus 3. The first strategy we're going to use is the y-intercept and slope. We know the y-intercept from the b value. This is going to be one of the points. So when we look at this one, we know our b value, or y-intercept, equals negative 3. The next thing we're going to do is look at the slope. And we're going to use this slope to go for a little walk. The run and the rise given the 3 over 2. So we look at our slope, we got 3 over 2, which means we are going to walk 3 up and 2 to the right from any given point. So we write down our y-intercept first, which is negative 3, which is down here. And we go for that walk, 3 up, 1, 2, 3, and then 2 to the right, 1, 2. And we make a point. And we can repeat that as many times as we like and go from there. Now keep in mind Depending on how big the graph is and where your y-intercept is, you might not be able to move in one direction. In that case, you're going to consider a slope of the opposite signs, because -3 over -2 is still 3 over 2. So in this case, we would go down 3 and to the left 2. So we would just go down 3 and then to the left 2. Noticing that still falls on the line. So let's fill it in. Take our line. I'm going to straighten this one up a little bit. But there we go. So let's look at strategy 2. You can use the y-intercept to find a point. We know that point would be 0 and b, because that's what the x is for y-intercept. So the point for us would be 0 and -3. Then we're going to substitute a value of x and solve for what y must be. This will give you your second point. So we get to pick a number. Let's pick x equals 2. So when we substitute in 2, we get y 3 over 2 times 2 minus 3, and y equals 3 minus 3, which equals 0. So when x equals 2, y equals 0. So we're going to find those on the graph. We get -3 and 2, and then we line those up as well. And there we go. So either way, we end up with the same graph. So now we're looking at an example where we have the graph of y equals 3 over 2x minus 3. But now we've turned the graph into this. Y is less than 3 over 2x minus 3. Well, let's think about what less than means. It means that the value of y we choose is going to be less than any value that this defines. In other words, it's going to be less than the line. Well, less than the line is going to be below the line. So we are going to be picking values below or equal to this line, because we have less than or equal. So this means that if we shade in a region up to and including the line, and we pick any point inside this region, it will make it true. So when we do these linear inequalities, or any inequality, we want to do that test point. So we're going to pick a point inside the region that we shaded. Let's pick 4 and -2. And let's substitute it into our linear inequality. So y is -2, less than 3 over 2, pick 4, minus 3, and let's see, 3 times 4 over 2 is 6. -2 is less than or equal to 6 minus 3 is 3. And sure enough, this statement holds true. So the point 4 and -2, which is in the test region, is true. And for the next example, it says graph the inequalities shown below. Y is greater than or equal to negative x plus 3. Well, the first thing we know is that the b equals 3, or the y-intercept. And we know the slope, which equals m, equals -1. Now we can write -1 in many ways. We can say just -1. We can say -1 over 1, or we can say 1 over -1. And this gives us the rise over the run. So let's start by graphing that line. So we find our y-intercept of 3, and we're going to go for a little walk up 1 and to the left -1. Well, if we do that, up 1 to the left, it's going to give us something like this. So now we got to figure out the shading. Well, in this one, it says that y is greater than or equal to the line. So it means we're including the line in anything above it. So when we do the shading for this one, we need to shade up. Here we go. So the negative x plus 3 is this line right here, and that's our boundary. And the greater than or equal to is the shaded region above the line, and this area here is the solution region or set. Now let's pick a value in our solution region to test to see if this is indeed the right area to choose. Well, I'm going to pick 6 and 2. Or sorry, let's pick 6 and 6. So if we pick 6 and 6 and substitute it in, we get 6 is greater than or equal to -6 plus 3, or 6 is greater than or equal to -3. And that's true. But what if we pick a point in the region that is not shaded? What if we picked -6 and -2? Well, in this case, when we did it, we would get, sorry, +2. Let's keep it at -2. So we would do -6 is greater than or equal to -2, the negative of -2 plus 3. Well, we get -6 greater than or equal to, the negative of a negative is positive, and 2 plus 3, that gives us 5. And when we look at -6, it is not greater than 5. So we can just tell that this is definitely not a solution in the region. Now, sometimes when we do these inequalities, and we've seen this before, we need to solve the inequality for y first because the x and y are on the same side. Now, we do this in the same way we would for an equation with one very, very important difference. If you multiply or divide both sides of an inequality by a negative number, you must flip the inequality or flip the sign. In other words, if it's less than, it becomes greater than, or if it's greater than, it becomes less than. So when you multiply or divide both signs by a negative, you change the sign of both sides by making both sides have the opposite sign as they used to do. You change the direction of the inequality. So let's consider these cases here. For instance, let's say we have a positive number that's greater than a negative number. Let's say 3 is greater than negative 2. And if we multiply both sides by negative 1, well, that gives us negative 3 and positive 2. Well, now negative 3 is no longer greater than negative 2, so we have to change the sign. Let's look at two positive numbers. Let's say 3 is greater than 2. That statement is true. But now let's multiply both sides by a negative number, negative 1. This becomes negative 3 and negative 2. And remember, on a number line, on the negative side, the negative 3 is here to the left, which means negative 3 is less than. And what if we had a negative 2 that is greater than another negative number? Well, that has to be to the left. So let's say negative 3. If we multiply both of these by a negative number, negative 1, we get 2 and 3. And now 2 is less than 3. So this is why we must flip the sign, because multiplying or dividing by negative numbers will change which side is actually bigger. So let's look at an example. So let's graph the inequality shown below. Minus 2y less than 8x minus 2. Well, the first thing we want to do is we want to isolate the y. So in this case, we're dividing both sides by negative 2. And not only both sides, but all terms by negative 2. So negative 2 over negative 2 gives us a y. 8 divided by negative 2, that gives us a negative 4. And negative 2 by negative 2 is a plus 2. Plus 1, sorry. Now in this case, I want to change the sign because I divided by that negative number. So take care when you do this that you check that if you multiply or divide, you flip the sign. Now this part here, this negative 4x plus 1, that is our boundary of the solution region. But we have to decide, is it included? Because this is greater than, this means it is not included, and therefore the boundary line is going to be a dashed line. So when we graph this thing, well, let's do that. The b value is 1. The b equals 1, which means that's the y-intercept. The slope is -4, which means we can go for a little walk. -4 over 1. So in other words, down 4 to the right 1. So 1, 2, let's get a red pen. 1, 2, 3, 4, and to the right 1. So there's another point. We're going to connect those together. Let's just move that up. Need a little longer. But because it's not included, we're going to change this to a dashed line. This indicates that while the line is the boundary, all the solutions can be as close to it, but it can't equal it, just like our inequality says here. Now we see that y is greater than the boundary, so that means we have to shade above the line. So we have to shade up. So let's go ahead and do that. And there you go. Now remember, you can pause the video at any time to catch up on some of these drawings. I realize they do take time. So let's take a test point. Let's go back to good old 6 and 6. Well, when we take our value, we're going to go -2 times our y value, which is 6, is less than 8 times our x value minus 2. Let's see if that holds true. We get -2 times 6 is -12, less than 48 minus 2, and -2 less than 48 minus 2 is 46, and this is 100% true. So this tells us we've done things right. Let's look at the next example. In this one, we've been given the graph and we want to determine the inequality. So that must mean we first have to determine the equation to the boundary line. So we need to find the boundary line first, which means we need to know the y-intercept and we need to know the slope. Well, the y-intercept, looking at the graph, is 1. It's positive 1. And from there, we can determine the slope by going for a little walk. We're going to walk up till we see, or down until we see another crosshair. And what I mean by that is a point that intersects two of the grid lines. So I'm going to go from a walk from these 2 points. Well, if I start at the lower point, I go up 1, 2, and 3. So my rise is 3, and my run is to the left. So my run is -1, and 3 divided by -1 is -3. So my boundary line is of the form 3x, or -3x, plus 1. Now we have to determine what goes between the y and the -3x plus 1. Well, when we look at the graph, we can see that it is shaded above the line. And because this is a dashed line, it's not included. So this means that y is greater than, but not equal to, -3. So now I want you to take a turn. Go ahead over to your practice work and try questions 1A and 2D. Remember, it's always good to let your teacher know how you're doing to keep in touch. Send an email, book a meeting if you're having trouble. Okay, let's move on and crank it up a notch. This time, we're going to be looking at quadratics. Now remember, we're still interested in the regions where XY combinations make the inequality true. Nothing has changed about the process. It's just now we're dealing rather with lines with quadratic functions. So let's start by graphing the quadratic function y greater than or equal to x squared. Well, we know that this x squared is now the boundary line. So we have to graph that first. We also have to decide if it's a solid line or a dashed line. Well, because this is greater than or equal, we know it's a solid boundary line. So let's start by creating a quick table of values so that we can get a few ordered pairs to graph for this. Change that up a bit. Pick our x, put out our y. So I like to pick pretty easy numbers. I'm going to go with -3, -2, -1, 0, 1, 2, and 3. Now, because this is x squared, all we're doing is squaring those values. And I won't go through all the process for each one, but notice what goes down must come up in a quadratic or vice versa. So let's plot these points. We're old hands at doing this now. And we're going to carefully draw in the line. Okay, so notice, draw it in the graph, very familiar graph. It's a solid line because of the greater than or equal to, and now we have to determine the shading. Well, because it's greater than, it has to be above the line no matter what area we're looking in. So it's going to be in the region up. So let's go ahead and shade that in. So there we go. And like always, we're going to do a test point. Let's test something on the y-axis. Let's test 0 and 5 for our test. Well, we're just going to take our 5, replace it to the y, fill in our 0 for the x, square it, and we get 5 is greater than equal to 0, which is 100% true. So that means that we have shaded it correctly. Okay, in this question, we're being asked to match the quadratic inequality shown to the right with its graph shown to the left. Well, let's go and look at some of these graphs and see if we can determine some very important characteristics. Let's look at this graph right here. Well, here I can see, and I'm just going to change the thickness of my pen a little bit because it's hard to see. I can see that regardless of where I am on this graph, the region is shaded below the line. So we know it's y is less than the line, less than the boundary line. The other thing I notice is that it's a solid line. So more importantly, we know that this one is y is less than or equal to the boundary line. Now let's look at this one. Well, in this one, it's shaded above the boundary line. So this means that y is at least greater than the boundary line. And when we check out if it's a solid or dash line, it's dashed. So we know that y is only greater. It cannot be equal to the boundary line. Now with this one, it's the same. It's y is greater than, but more importantly here, it's a solid line. So that means y is greater than or equal to, and you've probably already guessed by now that this one is very similar to the first one. It's y is less than, but not equal to. So knowing that, when we look at the graphs, we can say that for the first graph right here, we have y greater than. This means that this one must be A. For this one, we have y less than, so we know that it must be B. And for C, which is y less than or equal to, that means this first one here is C, which means y greater than or equal to is D. Let's move on. So in this one, we're asked to sketch the inequality for the example below. In this one, let's pick apart some of the key features. Well, the first thing I notice that is I have greater than or equal to the line, which means I have a solid boundary line. And the shading of this we know is going to be above the line because it's greater than. Now let's graph it. Now let's pull out some of that information we used from math from the first unit. This equation is in vertex form. Remember, vertex form is y equals a times x minus p squared plus q, where p and q are the vertex. Well, in this case, our vertex p and q is 1 and 4. Then when we look at the a value, remember the a tells us if a is greater than 0, it opens up. And if a is less than 0, it opens down. Well, in this case, our a value, which is equal to -2, is less than 0, so it opens down. So we have our vertex at 1 and 4. Okay, so let's pick a couple points. Let's pick -1, 0. We've already got 1 because for the vertex, and 2 and 3. Well, when we put -1 in, we get -2 times -1 minus 1 is -2 squared plus 4. This is going to give us -8 because -2 squared is 4. -2 times +4 is -8 plus 4, which equals -4. When we put 0 in, we get 2. I won't do the calculations. When we put 2 in, we get 2. And when we put 3 in, we get -4. So plotting these points, 0 and 2, 2 and 2, -1, -4, and then 3 and -4. So this is going to be our boundary line. So let's draw that in. So now there's the line. And notice that we have a solid line, and the shading now has to be above the line. So we have to shade up. So go ahead and shade that in. And let's pick a couple of test points. Now, the first test point, let's say we're going to try 4 and 4. So when I have y equal to 4, 4 is greater than -2 times 4 minus 1 squared plus 4. So that means 4 is greater than or equal to -2 times 3 squared plus 4. 4 is greater than or equal to -2 times 9 plus 4. And 4 is greater than or equal to -18 plus 4, which is greater than or equal to -14. And sure enough, that's true. Now let's do one in the region that is not shaded. 1 and -1. That's in the region that's not shaded. So let's go ahead and put that in, and we get -2 times 1 minus 1 squared plus 4. Well, that gives us -1 greater than or equal to -2 times 0. That's a fun one. Makes things easy. And -1 greater than or equal to 4. And that is not true. Therefore, we know that the region that we've not shaded is also correct. Now let's go ahead in the next one and graph the corresponding equality for this. So now what we need to do, we need to determine the boundary line based on our graph. So let's start by looking at this quadratic. Remember that when we have a quadratic in vertex form, we're going to start by inserting the P and the Q in first. So let's look, what do we have as a P and a Q? Well, this is our vertex, so that means our P is 0 and our Q is -2. So we can start by inserting those, and x minus 0 is just 0, so this is x squared, minus 2 because it's plus a -2, so we're going to say y equals a times x squared minus 2. But we still need to determine a. Well, we're going to do that by picking another point on the graph. Let's pick this one, which is 2 and 2. We're going to substitute the y for 2, and we're going to substitute the x for 2, and we're going to isolate the a. So we're going to add 2 to both sides to give us 4 equals a times 2 squared, which is 4, dividing both sides by 4. We have an a that equals 1. So our equation is y x squared. Well, let's write it somewhere else here. Y x squared minus 2. Now we have to determine the boundary line. Well, this tells us that it's not included. And because it's shaded below, it tells us that the y must be less than but not equal to the boundary line. So y is less than x squared minus 2. So let's go ahead and do a little bit of a test. We're going to test one of them inside the boundary region. Let's pick 5 and 5. Well, when y is less than 5 squared minus 2, 5 is less than 25 minus 2, or 5 is less than 23. We're good. Let's test one inside. Let's pick 0 and 5. I'm sorry, not inside, outside the boundary region. So we have here 5 is less than 0 squared minus 2, or 5 is less than negative 2, and certain enough that does not work. And so this shaded area represents the solution set for y less than x squared minus 2. And the last one. Hannah owns a small business producing red and green candles. She can make up to 10 candles per day. Write an inequality that represents how many types of candles can be produced per day. Define your variables and state any limitations that there must be on the variables. Well, we have two things happening here. They tell us the kinds of candles, red and green, and they say she can make up to 10 candles. Well, starting with variables, we can say let red R equal, R is going to be the number of red candles, and green is going to be G. So that's the number of green candles. Pretty straightforward. Now every day she's going to make some red or some green or some combination of both. And she's going to make up to 10. Well, up to 10 means she can make anything less than 10, or she can make it equal to 10. So depending on how many she makes, so let's say R plus G, which would be the total number of candles she makes, it could be less than 10, but it could also be equal to 10. So R plus G is going to be less than or equal to 10. But then they ask us to state any limitations on the variables. Now remember, in problem solving, the values we pick must be realistic to the question. Here we have things that can be counted. Candles. We can't have, she's never going to make 1.5 candles. It's going to be 1, 2, 3, or 4. So for this one, we're going to say that the R must be greater than or equal to 0, but R is an element of the integer numbers. For the G, it's going to be the same. G must be greater than or equal to 0, but G must be also an integer value. Well, let's finish this up today. Remember, it's time to get some practicing done. This is the one where we want you to check in. Try questions 2I and 3D and email your teacher to let them know how you've done. And after you finish that, it's homework time. I want you to practice as many as you can and making sure you get in touch with your teacher if you're struggling. Well, that's the end of the lesson, everyone. If you have questions, let us know. Otherwise, have a great rest of your day. Take care.